Welcome to this talk. I am going to present our work on constructing smart agriculture applications using local development tools. My name is Nyabisa Oteyo, together with my collaborators Scull, Jesse, Stephen, Wolfgang, and Elisa. Smart agriculture applications are a promising path to the future of farming and food production systems. These applications rely on sensors collecting data and sending it to mobile devices to influence the decisions made by farmers, such as commencing to prepare land when rain is predicted in the near future. From a deployment point of view, smart agriculture applications embrace a distributed setting. For example, different sensors for temperature, humidity, and soil moisture can be installed in a farm to collect and send data to mobile devices. The distributed setting makes constructing smart agriculture applications a complex undertaking, especially to domain experts. Local development tools have risen that domain experts can use to construct smart agriculture applications. By definition, the local development tools are visual programming environments that permit domain experts to produce software systems. Constructing software using the local development tools can be intuitive to the domain experts. However, the local development tools need to support domain-specific properties to allow constructing software for that domain. In this work, we focus on the smart agriculture domain. We identify different properties that the local development tool should support to allow constructing smart agriculture applications. These properties include web programming environment that allows domain experts to focus less on installing software development toolkits. Sensing capabilities to allow monitoring environmental conditions in farms. Offline accessibility to store data collected from sensors when the network connections become unavailable. Computation at the edge to transform data collected from sensors near the source. And lastly, low infrastructure networking to allow sensors to communicate directly to the applications running on mobile devices. We use the identified properties to compare different local development tools that exist in the literature. Compared to the rest of the local development tools, only Discover supports offline accessibility through in-database storage. In-database storage is limited to devices that have more memory for data storage. And none of the existing tools offers support for computation at the edge and low infrastructure networking. In this work, we focus on Discover and augment it with components to form Discover K. We focus on Discover because, compared with the rest of the local development tools, it already supports more properties that we can use to implement smart agriculture applications. Discover K is an extension of Discover that supports offline accessibility at the edge, computation at the edge, and low infrastructure networking. We added a new scope to house the components that execute at the edge. The new scope is highlighted in yellow color in this illustration. Note that by connecting components with different execution scopes, automatically yields a distributed application. The example that we show here has blue components that execute at the edge, black components that execute on the mobile devices, gray components that execute on the web dashboard, and light gray components that execute on the server. To motivate Discover K, we considered a modern farm where we need to track the number of sensors that are installed in the farm, read and monitor farm conditions such as soil moisture, temperature, and humidity, accumulate data from sensors, filter data coming from different sensors, generate and show notifications based on set thresholds, compute metrics for farm conditions at the edge, and store data at the edge when the network connections become unavailable. We implement these requirements into components in Discover K that can support implementing smart agriculture use cases. To explain Discover K, let us consider an application example in which we need to read the soil moisture, compute the average soil moisture at the edge, buffer data at the edge when the network becomes unavailable, generate and show notifications, track devices and aggregate data, and lastly, filter data for specific devices. To read the soil moisture conditions and perform computations at the edge, we implemented the read soil moisture and compute edge average components. The two components run on the edge. The read soil moisture data from sensors and sends it to the compute edge average component. In this example, we show two components that run on the edge to read soil moisture and compute the average soil moisture at the edge. The compute edge average component receives a stream of soil moisture data and computes a running average that it sends to the mobile device. Note that the compute edge average component is connected directly to the black component that runs on the mobile. To store data at the edge, we implemented the buffer cache component that runs at the edge and stores data in memory when the network becomes unavailable. The stored data is sent to the mobile device when the network connection becomes available. The size of data to store can be specified as a configuration setting for the component. Generating notifications requires a threshold that can be compared with soil moisture data. We implemented the set threshold component for setting the threshold, the compare component for comparing the set threshold with the incoming data, and lastly, the generate and show alert component that generates and shows notifications as pop-up messages. The output from the compare component triggers the generate and show alert component. As noted before, it is important to know the number of connected sensors in a farm. We implemented the connected devices component that receives messages from the edge with the identities of connected devices. The component filters the identities of the devices to remove duplicates and returns the number of unique identities that corresponds to the number of active and connected devices. The component uses WebSockets to keep the number of connected devices real time. We accumulate data from different sensors to have a global view of the farm. To accomplish this, we use the device accumulator component. The component runs on the mobile device and takes as a configuration setting the number of devices from which to accumulate data. When the specified number is reached, the component starts to accumulate data. The component uses a map to store the identity of the data source and its payload. The specific payload for a specific device for which data is accumulated can be filtered using the unwrap for specific device component. This component takes as a configuration setting the identity of the device to filter data for. To validate our work, we adopted a scenario-based approach. This approach describes a set of interactions between different actors in a system as a sequence of interaction steps. We conceptualize our validation scenarios as a flow of computation tasks. In this validation, we seek to answer two questions. One, how Discover K fulfills the requirements and properties of the implemented scenarios. And two, how Discover K as a local development tool can be used to improve the development of smart agriculture applications. Our first validation scenario is focused on monitoring soil moisture and temperature. The aim is to track the average soil moisture and temperature, compute the soil heat capacity metric at the edge, store data at the edge when the network becomes unavailable, send data directly from sensors to the mobile application, track the global view of the monitored parameters, track data for specific sensors, and generate and show notifications. The overview of the application flow graph for monitoring soil moisture and temperature shows the different implemented application requirements. Remember that the blue components run and perform computation at the edge, and the black components run on the mobile. The blue components talk directly to the black components. The overview of the resulting smart agriculture application for monitoring soil moisture and temperature is shown in parts 1 and 2. Receiving data from sensors deployed to plants in a pot in part 3. We use a Wi-Fi network for the sensors to talk with the application on the mobile phone. Our second scenario focuses on monitoring humidity and collecting data into a database. The aim is to track the average humidity data on a gauge chart, track humidity over time on a line chart, notify when the humidity level goes beyond the set threshold, collect humidity data into a database, and create reports as CSV files. In this section, we show the application flow graph for monitoring humidity and collecting data into a database, and the different sections that fulfill the requirements of the application. We inherit the observation database observation to table and display as table components from this scopper. Parts A and B shows the mobile application overview for monitoring humidity and collecting data. The data collected is displayed on a web dashboard from which CSV reports can be generated as shown in parts C and D. Our last validation scenario focuses on tracking application data using quick response codes to monitor crop growth and development. In this scenario, the aim is to scan plant labels and invoke a survey for data collection, send data collected to a database, display collected data on a dashboard, and generate CSV reports. The flow graph and the overview of the resulting application are as shown in this section. The application graph is composed of 5 components. The read QR code component that reads the plant labels, observation pop-up survey component that generates the data collection survey, observation database component that saves the data collected into a database, observation to table component that converts the saved data into a list for display, and lastly, the display as table that displays the data from the database as a list. Part 1 shows the data collection survey, and part 2 shows the collected data displayed on a web dashboard as a list. Now that we have explained the validation scenarios, let us revisit the validation questions. In terms of fulfilling the requirements for the implemented scenarios, this Discover K offers components for sensing to monitor farm conditions, performing computations at the edge, i.e. near the sources of data, buffering data at the edge when communication networks become unavailable, and supporting low infrastructure networking such that sensors can talk directly with the applications running on mobile devices. In terms of improving the development of smart agriculture applications, Discover K supports techniques that hide away issues like memory management and distribution that can be hard to configure manually by domain experts. In summary, in this work, we have presented Discover K, our local development tool for constructing smart agriculture applications. We have motivated our work by identifying and implementing useful properties and components for constructing smart agriculture applications. We have explained the usefulness of the implemented properties and components. And lastly, we have explained the scenarios that we implemented to validate our work. As the conclusion, in this work, we propose Discover K that supports offline accessibility at the edge, computation at the edge, and low infrastructure networking that sensors can use to communicate with applications running on mobile devices without going through a centralized server. The visual components offered by Discover K can improve building smart agriculture applications. I welcome you to read the full paper, and for comments and suggestions, kindly get in touch with us through the provided email address.